Hello, everybody, and welcome to today's webinar presentation, Unleash the Hidden Value of Data with Data Lake Management Technology, brought to you by LexisNexis. I would like to introduce you to our presenters. Dr. Flavio Villanustre is the CISO and VP of Technology for LexisNexis Risk Solutions. In this position, he is responsible for information security, and he leads the HPCC Systems overall platform strategy and new product development. Dr. Villanustre is also involved in a number of projects involving big data integration, analytics, and business intelligence. In addition to this, Dr. Villanustre has been involved with the open source community for more than 15 years through multiple initiatives. Prior to his technology career, Dr. Villanustre was a neurosurgeon. And then our second presenter today is Roger, and Roger is a senior architect working on the machine learning team at LexisNexis Risk Solutions. He joined HPCC Systems from CA Technologies. Roger has been involved in the implementation and utilization of machine learning and AI techniques for many years, and he has more than 20 patents in the diverse areas of software technology. And from that, I would like to pass it over to Flavio.
Thank you very much. And hello, everyone, again. We are going to be covering an introduction on our HPCC Systems open source platform and a little bit of an easing into the specific topic of data lakes. I don't expect to take much time, but I will give you an overview of the core aspects of the problem of data integration, how we deal with it with our platform. Before we start, I think everyone would be familiar with the data integration funnel. This is how data is acquired and integrated in a way that the data elements that are redundant are eliminated, the noise is fixed, is reduced, the typos, the mistakes in the data are also eliminated, and the data is built into a consistent platform of data that can be used to really extract truth values from the data. Essentially, you are building in this process a source of ground truth that you can use to then build any solutions on top of it. If you look at the screen right now, there is a funnel there in the central portion of the screen with data coming in on the left-hand side. That data represents both unstructured and structured data. And as it comes in from the left and moves to the right, the volume of data decreases, but the density of information in the data increases. And when you get on the right-hand side, you can truly, again, build and deliver the solutions that you need to build, be this being data exploration or some formalized platforms to deliver data as products to someone, either internally or externally in the organization. We, in HPC Systems and LexisNexis Risk Solutions, we built an HPC Systems data lake, which is a platform that allows us to ingest all of this data, to perform all of these pipeline of data integration, which goes through data profiling, cleansing, normalization, standardization, and eventually linking of that data. And all of these central funnel is performed in the platform. Moreover, even the real-time data delivery on the right-hand side is delivered through the same platform. Again, this HPC Systems platform is open source and free. So it gives a good opportunity to everyone listening to this webinar on something that they can try without needing to invest any money to try it. And if it works, they can just use it as it is. So the key aspects of any data lake solution, but I say that this is what we have in our own data lake solution based on this HPC Systems open source platform, is represented here as a little bit of a water cycle. It's representing data and how we process the data to get the data into meaningful and useful information. For what we have built in HPCC Systems, we can say that we have something that offers a complete life cycle for data. And that includes, as we say on the left-hand side, the fact that we have a platform that can deal with both real-time data and also batch ingestion and delivery of data. we have APIs. We use, in general, standards as much as we can, and all of the application programming interface, all the APIs are also standard and using standard methodologies to communicate. We can scale with the platform from really megabytes to petabytes of data in a way that is seamless. So you can use commodity computers to expand horizontally. And more important nowadays, you can use public clouds, and you can just provision additional instances to expand your storage and your compute capability as required for your particular application. And certainly this gives us also the ability to provide a more seamless and integrated delivery solution for all stakeholders. The fact that the platform is a single consistent platform, and the fact that it's consistent across all of the components means that you can use the same exact methodology to develop all of your steps in this data pipeline. From the very beginning, where you just understand your data by profiling, all the way up to the end where you deliver the data, allowing other systems to query the data or even represent the data in charts and any other graphical interfaces. Now, the way we do this in a manner that is efficient and effective is by building this layered set of components, where at the very bottom we have this HPCC Systems platform. This platform, again, is a software platform that runs on commodity hardware. It has two main components. One component, which is called Thor, on the left-hand side. Thor is the massive data integration data lake engine. And another component on the right-hand side called REXIE, which provides for real-time data delivery. In your funnel, the biggest chunk of your funnel is Thor, and the right-hand side, where you deliver the data real-time, highly concurrently, and highly availably, is done by REXIE. Now, these two components provide the underlying infrastructure and all of the workflow capabilities and all of the standard interfaces, and they integrate with other technologies. We rely on other open source technologies to help us deliver aspects of the data lifecycle that are better tackled by other systems. For example, the platform has good integration with TensorFlow. So if you have already developed some deep learning applications, for example, based on TensorFlow, it is trivial to use this directly on HPCC if your data is being managed by HPCC. This gives you the best of both worlds, where you have a data management platform and data lake solution that gives you all of the data management and data lake capabilities, but also you do not need to move the data out once you need to apply your deep learning strategy, because that model can be directly applied on the data in that data lake. On top of that, you will see that we have in an area where it says common language on the left-hand side. That common language that we have across the platform is called ECL. It's a declarative data flow language, and declarative, not unlike SQL. This is why porting ECL to SQL and vice versa is fairly simple as well. And ECL is this type of unified human programming interface across the entire system. This allows a data analyst and a data scientist to encode certain data management strategies in a way that is, on one side, fairly high level, so it doesn't require them go out of the way to build this, and doesn't require a lot of effort. But on the other hand, it gives the machine enough information about the process for the machine to optimize it. So by using a high-level language, you are not leaving aside your ability to run something that is highly optimized and highly efficient on the systems that you're running, being that bare metal hardware or even the cloud environments. On top of that, we have built a number of applications and components that are also layered. So each one of these layers relies on the bottom layers to become more efficient. Each one of these sits in on the shoulders of the bottom layer. And this gives us a variety of capabilities, which I won't go through in detail, otherwise we wouldn't have enough time for Roger to go through this part. One of the components that is interesting to consider, for example, for your data ingest piece, this is as your data is getting into the lake and you're trying to understand what these data elements are, is the data profiling capabilities that HPCC brings. As you can see, there is a standard interface to HPCC called ECL Watch, ECL being that language that I mentioned before, and ECL Watch is a user interface, user management interface to the platform. And within ECL Watch, as you can see, you can access important information about every data set that you have processed in your system. And this is not just information about the metadata on the data set. This is not information just about the name of the fields or the number of fields. This is information about the semantics, about the content of the fields. This tells you about your data distributions. This allows you to find data holes or data that has been formatted in a way that is incorrect for the application that you are trying to implement, or data updates that don't conform to data considerations that you have made when you decided to build the application. This type of information being like this at your fingertips allows you to, first of all, understand the data that you're getting, even if it's the first time you get this data or if it's just an update, and also allows you to automate the data processing, taking into consideration the fact that the data sources that you're using might at some point in the future change, and you would like to know that change and potentially anticipate the adapting the application in a way that can be resilient for these data changes in the sources. Now, today, we couldn't do a good job at speaking about data lakes if we didn't talk about machine learning, because machine learning is becoming quite pervasive. And anything out there that is providing data management abilities needs to be able to integrate and provide machine learning capabilities as well. And in HPCC, in this HPCC Systems open source platform, we have built support for a number of machine learning capabilities, which covers pretty much every generic area machine learning that we use today. This includes all of the classical machine learning applications. This is unsupervised and supervised learning, and a number of those are implemented even natively in HPCC. And of course, all of the capabilities around deep learning, and many of these are supported through the integration with TensorFlow. TensorFlow is also another, in case you are not familiar with it, another open source project. In this case, Google has made available for encoding deep learning applications and neural network stacks, deep stacks. All of these, again, supported through the same seamless data lake approach. So you don't need to move your data out or jump through extra hoops to get your data analytics implemented on top of this data lake. So just to pass this to Roger, there are, I would say, three very important differentiators with HPCC systems as a platform for implementing data lakes. Certainly, the first one is that it's completely free, and free. This is in two ways. It's on one side, like free beer, is free of cost. It's open source. All of the source code is in GitHub. All of the binary and installers are all available and continues to evolve. And we release new versions every week and new releases every quarter, and even major releases every year. So it's very active. It has a fairly large community. It continues to be developed, and almost every major release includes a large number of new capabilities. So it's a really a platform that should not only get your needs today, but also cover your future needs as you evolve and also the platform evolves. It also has a number of out-of-the-box capabilities, and a large number of fairly large companies are using HPC systems as a platform for their own data lakes, which works two ways. One, it shows the capabilities and the resilience and the scalability of the platform on one side, but on the other side, it also brings all of those organizations as community members and contributors in many cases to a platform. So helps us continue to push the new capabilities, but also the ease of use and the consistency across the platform. This is a platform where you don't need to get involved into developing each one of the little components or integrating each one of the little products or systems, where all of this comes in a single package. And certainly less coding. Yeah, it's not that we don't like to code, we love to code, but all of the capabilities that come with HPCC come in an easy-to-use container platform. And as such, you can get away with almost no coding to do a fairly large number of standard things. And certainly you have the ability to code and expand and go beyond as much as you need. Without more preamble, I will let then Roger take over from here. Roger, the floor is yours.
Hi, everybody. Welcome to our webinar. Thank you for attending. I'm going to be talking a lot about data and its inherent, yet often elusive value. Data exists in many forms: numbers, text, image, and video, for example. The data available from public and private sources is increasing exponentially. We've all heard about big data and its promise, but we've often tried to apply the tools and techniques used for managing structured and limited data to tackle the ever-expanding mass of available data. We lacked an architecture and technology that's flexible and powerful enough to unleash the power of this data. Let's talk a little bit about value. As an information provider, I think of data as a commodity that can be developed, monetized, and sold. I'll never belittle that, but there are many forms of value that can be derived from data that are beyond monetization. Data has been used to find missing children, catch criminals, identify new materials in pharmaceuticals, understand the universe we live in, and literally save countless lives. It's hard to put a price on that. I'll talk about a modern architecture specifically designed for exploring, discovering, and extracting the value from these myriad, complex, and interwoven data sources. Let's start by taking a look at what we mean by data lake. Data lake is an architecture and methodology for managing complex data. Data lakes are used today by many successful businesses that make their living as providers of data. More and more enterprises are adopting data lake technology to manage their internal data so that it can be effectively leveraged for all aspects of their businesses, as well as their relationships with customers and suppliers. Data lakes are designed to handle complex data that may come from many sources and have many potential uses. It does not replace relational database systems for managing structured processes like accounting and payroll. Rather, it's optimized for the generation of value from the data produced by these and other sources of data. Realizing the value from any set of data is not a one-time thing. Value snowballs as data is refined, integrated, and analyzed. It's an incremental and continuous process. Some people think of data lakes as a playground for exploring data and looking for nuggets of value. Then those discoveries are transferred to another team to productize using a different system and architecture. In our view, that's a big mistake. Not only does it greatly delay the path from discovery to realization of value, but it hampers the discovery process itself, which must build upon the solid foundations of previously stabilized knowledge. We believe that data discovery and experimentation are important, but the path from the discovery to hardened production should be short and should not require a shift in technology. A data lake will continuously acquire data from many external sources and ingest it into the data lake. Data is usually stored in a simple, flat file-like format, such as basic disk files, or as a name addressable form, such as Amazon's S3. These are efficient forms for the types of processing done within the data lake. Data lakes begin with a few data sources and some ideas for enhancement, and these expand dramatically over time. Once the data is ingested, the process of enriching the data begins. This is an evolving, iterative process of refining the data to extract as much knowledge as possible. As with all human endeavors, knowledge accumulates iteratively as it builds upon itself. No matter how valuable the accumulated knowledge is, it's only useful if it can be made available to the various people that need it in a timely and efficient manner. The data delivery process ensures the data is made reliably available to the appropriate users. Finally, it's very important to have a process for curation, organizing, visualizing, and governing the data lake. There's a term for an uncurated data lake. It's known as a data swamp, and like its namesake, becomes an unpleasant and dangerous place to store your data and produces very little value. It's useful to contrast the database, data warehouse-centric approach with the data lake approach for dealing with complex data. In a typical database-centric approach, the needs of the users is assessed, and a schema is defined that meets those user needs. Then programs or scripts are written to take the various data sources and perform all of the transformations to merge and transform these sources into the final schema that all of the anticipated applications will use. If a new data source, application, or feature is needed, then the schema needs to be redesigned and agreed upon. Programs that load the database need to be rewritten, and all the applications need to be reassessed for breakage or enhancements. This creates a tremendous barrier to change, slows down the value realization, and costs dearly in development resources. The final schema is the only visible portion of the system. All of the transformation logic is hidden in the programs that populated it. Any aspects of the raw data that were not considered useful to the original application is not available to users until the schema is redefined. With data lake architecture, all of the various stages of refinement are available for use by developers, from raw data to final application data. This can be built upon at any time to create new analyses, new user perspectives, or new applications without involving other teams. The full enrichment path is visible, as well as the specific logic of each transformation. Let's look at some of the benefits of data lake technology. As we discussed, the raw and intermediate results, as well as final application data, are available for further value discovery and creation. This is necessary for a continuous value discovery process. New data sources, perspectives, and applications can easily be added to rapidly create value for the organization. Data lakes scale easily to any capacity. The use of flat files allows for maximum efficiency and parallelization. Forklift upgrades are not needed to scale capacity. It can be incrementally upgraded by adding servers. Data lakes provide visibility into the entire data refinement and delivery process. This allows knowledge to be built up layer by layer with a natural cascade of value. Development teams can also scale efficiently, without forced dependencies among teams or single points of contention. It is well documented that inter-team dependencies are the most common causes of project delays and cost overruns. I'll discuss later how these dependencies can be nearly eliminated using data lake technology. The depth of the synergies within a complex set of data are often underappreciated. These data sets are typically characterized by an ever-expanding set of sources, each with their own imperfections, nuances, and hidden gems of value. The data sets are usually very large and constantly expanding in scale and volume of change. None of us are smart enough to look at such a body of data and know where all the value is hidden. We typically start with some surface level synergies, put those into production, and with those as a basis, can see opportunities at the next level. This refinement process can continue indefinitely, and in many cases, new sources and opportunities will arise faster than we can utilize the value at hand. While we may never extract every nugget within our data, the process of discovery, extraction, continuous refinement, and productization will result in greater and greater value as time goes on. Let's take a look at some of the dimensions of data enrichment so that we can get a glimpse into the depth of this process. Imagine that we run Acme Cab Company out of New York City. We have our own data regarding rides, start time, end time, start location, end location, medallion number, and number of riders. We'll use this example as we look at these dimensions of data enrichment. The first and most obvious way to enrich data is by removing errors and inconsistencies within the data sets. All sources of data contain these idiosyncrasies. Businesses have been built on this aspect alone, ingesting public data and fixing these inaccuracies. For Acme, this refined data set may provide better insight into our operation and improve our decision processes. By adding statistical analysis, we can begin to see how a given day's traffic compares to typical usage. We can identify unusual flows and usage trends. We may be able to better allocate resources and position our cars. Coverage enrichment is the process of adding more data sources for the same type of data. If we can include other New York City cab companies, that could increase the general value of our data. Suppose we can access cab data from Chicago and Los Angeles. What if we could include Lyft and Uber data? The closer we come to encompassing the full scope of the given data set, the more the value increases. Breadth enrichment is about finding data that is in some way complementary to our existing data. Suppose we overlay GIS information about business addresses and other venues. Now we can begin to infer where passengers are coming from and going to. This starts to enable us to visualize flows of tourist and commercial activities across the city. Now we've begun to open the doors to prospective clients outside of the transportation sector. We can imagine many such overlays. Entity resolution can be a critical yet challenging type of enhancement. This involves translating tags in the data into a persistent identity. In some cases, this can be trivial. The medallion numbers of a cab has a fixed identity that may exist in the raw data. Often, however, entity resolution is much more difficult. What business is the writer going to, for example? Addresses may serve many businesses. Business names might not align from site to site. Sometimes entity resolution is definitive, but in many cases it requires statistical inference. While these inferences are never 100% reliable, perfection is seldom a prerequisite for value extraction. Many businesses thrive by producing data that's more accurate than other sources can offer, even if far from perfect. Generally, the more breadth and coverage available, the better these statistical inferences can be. Relationship resolution looks at associations between similar or dissimilar types of entities. In our example, travel could be mapped between pairs of businesses or between transportation hubs and venues. This can also be challenging yet very rewarding. In some cases, entity and relationship resolution may need to be done jointly, as certain entities can only be resolved as a function of the relationships that they occur in. Relationship mapping can be taken a step further using transitive associations. This is following a chain of relationships to produce inferences about an entity. Think of the chain of the various rides that a person may take during a day and how that may illuminate deeper patterns in the data. Qualitative analysis is used to categorize or classify entities or relationships. Is this trip personal, tourism, or business in nature? In some cases, these can be handled through a simple set of rules, but often machine learning is employed to determine qualitative attributes. Diagnostic analysis attempts to identify anomalies or other interesting conditions. Perhaps ride times can be used to indicate accidents or other disasters. Unusual spikes in usage might indicate errors in the allocation of vehicles. Finally, predictive analysis looks at the time or space variant relationships. Are certain business usage patterns among rides leading indicators for future economic or market conditions? Can they indicate the need for enhanced police or traffic control presence? Various machine learning and analytic techniques can be used to model these subtle interactions within the data. You can easily see that with time, effort, and creativity, our modest starting data lake could soon eclipse in value the company that started it. Let's change subjects from the nature of the data to the nature of the development process within a data lake. Recall that one of the hallmarks of data lake technology is the ability to scale. It can scale in terms of data volume and number of users, but just as importantly, can scale in terms of the development process. A very simple example will illustrate how data lakes allow many teams to develop at their own pace while avoiding dependencies. In our example, we start out with 2 data sets, and then we merge them together to produce a composite data set. This was done by a team in order to create the data needed for their application, which we call App 1. Now another team finds that data useful and builds another application, App 2, using the already merged data. A bit later, the App 2 teams acquires a third data set and wants to upgrade their application to include that data as well. They can upgrade the transformation to include this data, but that would require the App 1 team to stop the unrelated projects that they've been working on and analyze, retest, and repair their application so that it is not impacted by the change. This, of course, would force the App 2 team to delay the release until the App 1 team has had the chance to do this work. This type of dependency typically results in significant delays and cost overruns in both teams' projects. Data Lake offers a simple and powerful way to avoid such costly dependencies. The App 2 team simply creates a new merged dataset that includes the original merged dataset plus dataset 3. They can carry on with their project without in any way impacting the App 1 team. At a later date, the App 1 team may decide to do an upgrade and point their application to the second merged dataset as they make other changes. They can do this on their own time and without impacting the App 2 team. The implementation of a production data lake imposes some difficult technical challenges. People building an initial data lake often overlook the severity of these challenges and think, it's just flat files, so I can use Hadoop or in Python or Spark and I'll have a data lake. They underestimate the many factors involved in operating a data lake. Many types of users will be simultaneously using the data lake for exploration as well as productization. And important security and access control procedures must be available. Nearly all reliable sources of external data include covenants or privacy concerns that must be carefully managed. As the data lake generates value that many users come to depend on, the expense of any kind of outage goes up dramatically. Users may demand service level agreements with requirements in terms of uptime, data currency, coverage, and accuracy. The system must be resilient against equipment failures, loss of data, and often overlooked data corruption. As the number of sources increase, the likelihood goes up that an error at one of the data providers can cause significant corruption in your data. It is critical to be able to detect and rapidly roll back this corrupt data. Imagine in a database management system trying to undo all of the cascading errors caused by a corrupt data feed that perhaps was not discovered for some hours or days. Ingestion and enrichment are continuous processes. As new data arrives, it must be ingested, analyses run, and final data produced within the window of currency required. If data cannot be processed at the rate it is produced, then the analysis can get further and further behind. In a system that requires major upgrades to increase capacity, this can be very hard to manage and requires much reserve capacity. A successful data lake will have an ever-increasing population of users that may grow faster than infrastructure upgrades can keep up with. We've talked about the need for curation and governance. Without it, a data lake quickly devolves into a useless and dangerous swamp. Reusability and the ability to build on previous knowledge requires that the data transformation process and governance requirements are fully transparent. Finally, the data lake must tie into many of the same security and administrative systems used by other IT processes. HPCC Systems offers the most functional and robust solution for building production data lakes. It has been proven in a wide range of industries and operates some of the largest and most complex data lakes in the world. It's a time-tested solution that has sustained data lakes through tremendous evolution and expansion of both data and users. It's used in mission-critical applications with extremely tight service level requirements. HPCC Systems open source data lake solution can run on a basic laptop or can be scaled to thousands of servers and petabytes of data. It can run on-premise or in the cloud. It is secure and auditable, and is used to manage some of the most sensitive information for large and diverse user bases. The system includes a data curation subsystem called Tombolo, a single parallelized language ECL that controls the entire process, a rich library of machine learning and analytic methods, and fully scalable engines for data enrichment and delivery to end users. We'll discuss each of these in the following slides. Tombolo provides visibility into the data lake. It graphically depicts the datasets, transformations, access paths, and user queries for the entire data lake. Tombolo allows drill downs into the details of each of these elements, all the way down to the transformations that generate each piece of data. It provides a repository of documentation, governance needs, and procedures that allows data to be located, managed, understood, and reused. It supports the entire process from design to production and simultaneously allows private, non-curated exploration as well as production-hardened flows. The Enterprise Control Language, or ECL, is a powerful data flow language that defines the flow of data from end to end. It's a declarative language, which means that you tell it what to do with the data and not how to do it. In other words, you define the nature of the data you want to produce, and the compiler figures out how to make the appropriate transformation happen. That's a very important distinction for a number of reasons. First, it provides a transparent specification of the transformation without any obscuring technical details. Second, it allows the language to automatically parallelize the actions across any number of nodes. Add this to the fact that ECL is transparently compiled into C++ code, and you have the ability to process huge amounts of data very quickly. Further, there's no need to worry about technical issues such as memory management. ECL will run in memory when it can or automatically spill to disk when the data cannot fit in memory. ECL is transparent and easy to read and provides an excellent document describing the transformation required. ECL is a full-bodied transformation language with enough power to perform nearly any imaginable transformation. For example, it can even implement parallelized machine learning algorithms. ECL also allows simple embedding of other popular languages such as C++, Python, and Java, allowing the use of off-the-shelf analytic libraries written in those languages. HPCC Systems provides a broad set of analytic and machine learning libraries that are parallelized and optimized to run on the HPCC platform. These include a wide range of statistical methods, natural language processing, supervised and unsupervised machine learning, neural networks, and image and video processing. These methods allow the incorporation of any type of data into your data lake and the production of structured information from unstructured sources. The Thor data enrichment engine provides a secure, highly performant infrastructure for iterative data enrichment. It is secure, flexible, and scalable, and incorporates many advanced features needed to operate a production data lake. It handles the data flow from acquisition to final contents. Like the rest of the HPCC Systems platform, Thor can run on a single laptop up to thousands of servers, and in either an on-premise or cloud environment. It is fault-tolerant, able to handle processor failures or storage failures, and allows for incremental as well as batch processing. It provides mechanisms for automatic generational data backups and recovery in the event of corruption of received data. Thor transformations are defined using the powerful ECL language, which is automatically parallelized based on the defined size of the Thor cluster. Thor runs the appropriate transformations based on workflow rules, supporting manual, scheduled, and event-driven workflows. Thor also prepares the data for rapid access by the REXIE information delivery engine, including sophisticated indexing capabilities allowing random access into the enriched files from any direction. The REXIE data delivery engine delivers data to end users or applications using the most popular query protocols such as SOAP, REST, JSON, or SQL. It provides a secure API management environment with fast response times and is able to support diverse user communities of any size with multi-way scaling. The front end and back end processing can be independently scaled as needed. Like Thor, REXIE can be run on any size cluster, on-premise, or in the cloud. In the cloud, REXIE can automatically scale up and down to meet the fluctuating demands of the user community while minimizing costs. REXIE queries are defined using the same powerful ECL language as used by Thor, and the two systems interlock seamlessly. One button push causes the results of an ECL query to be published and available to users in one or all of the supported formats. REXIE is also commonly used for the real-time ingestion of data from Internet of Things devices that can then be enriched and made available to users. In closing, I want to emphasize the proven nature of data lake architecture. It's in use across a wide range of industries around the world. It is used by prominent information providers and large and small enterprises alike. Implementing and operating a data lake is not a trivial matter and requires substantial technology and expertise to be successful. HPCC Systems provides the most complete system for the creation and operation of data lakes. It is time-tested, secure, highly performant, open source, and free. It is easy to install and get started. A simple single system download can be up and running in minutes and is available on our website, hpccsystems.com. Thank you for taking the time to attend. We have some time for questions now.
And we already have a few that I'd like to begin with. Roger, this one's for you. You talked about the advantages of data lakes. What are some of the disadvantages?
Well, the primary disadvantages of data lakes are that you're trading off compute and storage resources for faster time to realize value. In other words, for opportunity costs, and also for improved development throughput. So if you look at what are the most expensive factors in IT development, it's really manpower and cost of opportunity, time to deliver your solutions. So basically, you're using more storage because you're storing intermediate and raw data and not just your final form. But storage is relatively cheap now compared to your IT resources.
Perfect. A second question is, even cloud providers are calling themselves as data lakes. How do you differentiate?
Well, it's really a matter of the infrastructure and the thoroughness of it. It's easy to call something a data lake, but to produce data, valuable data, continuously in real time with high service level agreements take a lot more technology than just some code running in a cloud environment.
Okay. A third question is, can data lake be used for AI solutions only, or are there more versatile options?
Oh, there are many uses of the data lake, as we pointed out. Everything from cleaning the data to statistical analysis, almost any processing you want to do to transform that data, a data lake is appropriate for. Machine learning and AI are just some of the tools available to produce more subtle value extraction from your data lake. So a lot of the value is produced by the simple basic block and tackle mechanisms of data cleaning and statistical analysis.
I think, if I may add one more component there, I think Roger, that answer was great. But I would say that also a data lake gets you a shorter time to implementation of any other data products that you need to build behind it. Because you don't need to go through the work in building all of these schemas and tables, as if you were using a traditional solution to do data management, you have the ability to pretty much ingest data, and as you ingest it, start building minimum viable products on that data, almost at the time of ingestion, and of course refine over time. So there are some intangible values to a data lake as well, which might not be just expressed in terms of what else you can do, but also on how fast you can try new things.
Thank you for that. Another question that an attendee is wondering is, how does a typical organization who is short of data scientists and data engineers pull resources off of other projects in order to get this set up? Additionally, how does one even begin on a project of such enormous scope like this?
Well, that's a very good question, because we all had that initial reaction to many technologies. Typically, what happens is that this starts small. You might have a particular need. You're not trying now to ingest some data into your, I don't know, data warehouse, and you realize that it's going to take some effort to do that. And instead of doing that, you build a small, very small data lake, and you just load that data into that data lake and start looking at the data there. You might realize that in order to be able to do good analysis on the data, you need to add some other data sets that you already have in your data warehouse. So you get to export those and move them there. And you may start with maybe very few or almost no resources dedicated to this, maybe just an experiment. But as you start getting value, you can free up resources, because those resources won't be doing as much work on your traditional data warehouse. They might not need to start building schemas as much, because you're getting your new data into the data lake. And eventually, you freed up so many of those resources that you can get them dedicated into the data lake and now do this bigger project where you decide to move the entire data warehouse into the data lake. I think in many cases, we've seen this as a type of ground up approach where these little efforts done by individuals end up re-upping a lot of benefits for the entire organization over time. Again, there needs to be some catalyzer, something that you're trying to do that is harder or expensive or difficult to do in your current data warehouse. And there's some individual that is creative enough and has some interest in success in this, that can get around and build this mini data lake. Over time, it is very likely that because of the success of that little incipient data lake, you can, based on that seed, build something that is far more comprehensive, and eventually you get the resources, because those resources will be freed up from everywhere else.
Perfect. That was very insightful. Another attendee's question is, how do you ensure privacy is maintained in any data lake solutions, including HPCC?
That is another great question, and this is the one that many times ends up blocking the development of data lakes. In the traditional solutions in data warehouses, we all went through the extreme and excruciating work on trying to build privacy protecting components around the data warehouse, which also has the same challenges that a data lake has. The main problem here, and it was also in data warehouses, is the fact that in order for all of these things to be really effective, you want more people to be exposed to this data, which in some way goes counterintuitive when it comes to protecting privacy, of course. So there are a few solutions there, and these solutions are not very different from what you have in your data warehouse, but these solutions have been most likely developed after your data warehouse was implemented. So these are things that you should be considering today, even if you're not moving to a data lake. And they apply to both sides. Some of those solutions are based on techniques to anonymize data. For example, a simple tokenization can go a long way. If you have fields of data that don't need to be exposed, if you're calculating, let me give you an example. If you're calculating your revenue based on region and product and branch in your business, and you have data about your customers, well, it is very unlikely that you need to expose the personal data of the payer in that customer, or the or the specific data of the customer information directly in that report. Maybe all you need to do is explore the data when it comes to numbers and regions and do different breakdowns and roll-ups. So you could tokenize, essentially replace some of those fields by either unique identifiers that represent nothing, tokens, artificial tokens, or you can just eliminate those fields or whatsoever, right? There are other cases where you cannot get away with tokenization, and that becomes a little bit more challenging. So if you do need to expose certain information, and sometimes you need to expose information as aggregates, but you don't want to expose the individual information, there are techniques that have been built for that. One of those is known as differential privacy. And all of these are supported in or can be implemented in modern data lakes, and not just HPCC systems and even your old data warehouse. And they are based on the fact that they can produce reports and aggregates of data elements without disclosing the specific information about the individual data elements in them. It's a far bigger discussion than what we can cover in this question, but there are solutions that can be used to protect privacy and yet provide the functionality that data lake brings. But they are certainly out of scope for this discussion. It would take another entire webinar for those.
Okay, this question is for both Roger and Flavio. How can ECL automatically parallelize with everything without intimate knowledge of the data?
I can take that first. So ECL as we mentioned, automatically parallelizes common usage patterns within the data. But there are some cases where there's knowledge about the data that allows you to do a better job of parallelization than the compiler can do itself. And this is really one of the strengths of ECL. It allows you to very readily and easily override the default parallelization techniques with a custom one specific to your data, and it will produce very good performance without doing that, but you can optimize the performance further by giving the compiler hints as to the nature of the data and how it can be best parallelized. And that's a very mature and important aspect of ECL.
And going on top of that, Roger, can you describe how ECL might compare to another language?
Well, it's quite a bit different from your traditional programming languages like C and Python and such. It's a declarative language. If you know SQL, SQL is a declarative language. It's a data flow language. Lets you define the data that you want as opposed to the processing that that needs to go through to get that data. So the best analogy I can make is that it's SQL on steroids.
I would add that if you're familiar with if you're familiar with the Scala, it also flows in a similar way. So it's again another declarative language. Other modern languages that could be compared with ECL are Clojure, which is a Lisp derivative that runs on the JVM too. That's as well, and also functional languages that use the same type of declarative. It's a denotational type of language. As Roger said very well, you express what you need rather than how to do it, and the language does it. You don't get involved in the flow of the program on the flow control. You get only defining what the thing should be. I have this data set, I want it sorted. So you said sort this data set. You don't tell it how to sort it. You don't need to get into the details on how to implement a bubble sort or a merge sort. And the same thing applies to other functions like projecting fields and contents, or remapping them, transforming them as you project them, performing roll-ups. All of these things are again things that you express as what you need. And if you're familiar with the spreadsheet, this is the same thing. In the spreadsheet, you define the formula, and then the rows are updated automatically. And if you change a row anywhere, all of the rows that are depending on that row that change, the data dependencies are key, and they are all implicit. So you don't need to go specifying what specific data dependencies are there. The system will find them. Again, Excel spreadsheets, this is another good example of a declarative programming model.
Okay, so we have 3 minutes left, and I've got 2 more questions for you both. This one's for Flavio. At the beginning of the presentation, you mentioned that this platform is free to the open source community. Which aspects of that are free?
The entire platform is free. It's open source. All of the source code is licensed under an Apache 2.0 license. All of the documentation is licensed under a Creative Commons license. There are no restrictions. There is nothing that is hidden or is kept proprietary. There are no proprietary components linked into it either. So the entire platform is free. All of the source code, all of the binary installers, all of the packages. There are no restrictions in any of the components that we presented today, and there are no special commercial requirements or any other closed source or proprietary components there. Certainly, there are maybe companies that could sell services on HPCC, and we have known of a few of them that are doing that, which is a good thing because it helps community members that require some special requirements on development or implementation of things. But again, all of the components and the entire platform is completely free and open. So there are no strings attached, and there is no impediment or obstacle for you to try as much as you want.
Okay, and one final question comes from the audience, and it reads, we have an Oracle database as a data source, and our application is an information management system. How can we use data lake in this case?
I'll take that
That's
one.
a very good question. Okay, Roger, I'll let you take it. Yeah.
Okay. Essentially, just think of your Oracle system as a source for data, as one potential source of data, and you can then extract the data from it, readily ingest it from within the data lake, and analyze it any way you want. Begin to really extract new value from that same data. Combine it with other sources, combine it with public sources, and you can start to really realize some incredible value.
Perfect. And with that, I would like to thank both Roger and Flavio for a great presentation. I would also like to thank LexisNexis for providing the audience with a great webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career and that you're staying safe out there. Thank you and have a great day.
Thank you.
Thank you.